Let's now have a look at acceleration. We talked about before and defined angular velocity. Now, the problems we look at all have uniform circular motion. Okay, so that's when it moves with a constant angular velocity. So you'd be thinking, oh, hang on, if it has constant angular velocity, then surely it has no acceleration. And that's true as far as angular motion goes. But linear motion, there's always a change because you're changing direction. So even though the actual magnitude of the velocity is constant, the direction is changing. So it will create a change in velocity. So let's have a look. Here's our circle. And I'm going to move from A to P, as I say, constant angular velocity. Now, we know acceleration is change in velocity with respect to time. Now, at A, yes, the magnitude is v, but we're going off in that direction of the blue line there. At P, I've called it v dash, but it's going off in a different direction. So if I think of them like vectors, so v is going that way, v dash is going that way, so therefore that red line must be the change in velocity. Okay. Well, let's just work that out. That angle there is theta, and we can do that simply with geometry because we know tangents are perpendicular to radius and so on. So it's easy to show that that angle would be theta. Now, that triangle is going to be similar to triangle AOP because remember I said the magnitude of the velocities is going to be the same. So I've got an isosceles triangle where the angle up here is theta. Well, OAP also is an isosceles triangle where the angle is theta. So there's the two triangles. So changing V over AP must be the same as V over R, ratio of sides in similar triangles. Rearranging that, so multiply by AP. Change in velocity with respect to time, so change in velocity over change in time is acceleration. So if we now sub in for change in velocity, I get V times AP over R times the change in time. Well, as that approaches zero, because remember our change in direction is going to be like really quick. The time between them is so close to zero because you're just constantly changing direction when you're going in a circle. So as t approaches zero, then the length of AP would actually be pretty close to the length of the arc AP because you've hardly moved. So we know that the acceleration will be the limit as delta t approaches zero of v times the arc of AP, so the length of the arc, over r delta t. All right, so distance equals speed times time. So arc AP, which is the distance, will equal v, not r, v times delta t. So if I now sub that in, I now get acceleration is the limit as delta t approaches zero of v times v delta t over r times delta t. Well, the delta t's now cancel, and I simply get v squared on r. Well, there's nowhere to substitute in the delta t now, because this is just going to be a constant with reference, and we get the lovely formula, acceleration is v squared on r. Now, as I say, that's quite a long way of going about proving that using vectors and what have you, but I think it's just lovely how it ends up falling out like that, which is what we want. So what we need to know, of course, is that the acceleration in uniform circular motion has magnitude v squared on r. Now the direction, if you remember going back to that red vector, the direction always ends up going towards the centre. It doesn't matter where you pick the vectors, the resultant vector, that red vector, will always be directed towards the centre of the circle. Okay, acceleration involved then in uniform circular motion. We know acceleration is v squared on r. That's if I'm using linear velocity. If I was to substitute in v equals r omega angular velocity, then the acceleration would be r omega squared is the formula if we're using angular velocity. But remember we said in extension 2 we're more interested in forces rather than acceleration. So the forces involved in circular motion, well, force is just mass times acceleration. So we have this mv squared on r, which you might recognise, or if we're using angular velocity, it's mr omega squared. Okay, so here's a question back from 2003. Particle, mass m, constant angular velocity, circle radius r. At any particular point, its position is given. So they're using the parametrics of the circle. R cos theta, R sine theta, where theta is omega t. Show that there is an inward radial force of magnitude mr omega squared acting on P. So in other words, they're asking us to prove our force here. We don't have to do it like I just did with vectors, as I say. We're going to do it via the parametrics, and it comes out quite nicely. So, okay, here's our path, P. So the parametrics, the x-coordinate is r cos theta, theta being the angle changing at the centre. Y is r sine theta. And if we do a bit like projectile motion really now, we've broken it up into two components, vertical and horizontal, and we work on each bit. So x is r cos theta, y is r sine theta. Well, if I differentiate with respect to time, unfortunately my variable is theta, so I can't differentiate with respect to time, I have to differentiate with respect to theta. But using implicit differentiation, I then say, well, times the theta to t, r of course being constant, so we don't have to worry about that. But the theta to t, of course, is angular velocity. So we get that the velocity in the x direction, the linear velocity, is minus r omega sine theta. I can do a similar thing over at y, and we get r omega cos theta. Differentiate again to get the acceleration, and the same thing happens. Omega, remember, is a constant, because we said we're travelling with constant angular velocity. So the only variable here is theta. Can't differentiate with respect to time, so differentiate with respect to theta. Implicit differentiation, multiply it by to theta to t, so exactly what I just did. But the theta to t is omega, so I now get minus r omega squared cos theta. But I then do something here. I notice, I say, well, hang on a sec, x was r cos theta, so I can sub that in and say it's just minus omega squared x, which is quite interesting when you look at it. Hopefully that's familiar. Simple harmonic motion. And in fact, circular motion, if you were to, instead of looking on top of a circular, something travelling with uniform circular motion, you'd see the circle if you looked on top of it. But if you were to look at it sideways, so all you're seeing is saying the x displacement, it would appear that the particle's travelling in simple harmonic motion. And exactly the same thing happens in the y, because of course it's a circle. So it shouldn't matter where I'm looking at it at the side, it's going to look exactly the same. It'll look like simple harmonic motion. So we know that the acceleration in the horizontal direction is minus omega squared x. We know in the vertical direction it's minus omega squared y. Let's resolve it to find the actual acceleration. So we need to work out this angle so we can see which direction it's travelling in, and we need to work out the actual value of the acceleration. Well, bit of Pythagoras. And we get acceleration squared is omega to the power of 4, because remember, of course, x squared plus y squared will be the radius squared, because that's the equation of the circle. And we get omega 4r squared, so the acceleration, and there's the formula that we were hoping to get, r omega squared. Now we need to work out the direction in which this force is going. It'll be going along the hypotenuse. We want to show that that actually is going to the centre. So there's the force. Well, we know that angle will be the inverse tan of y double dot over x double dot. So that'll be the inverse tan of y over x, because the omega squareds and the minus cancel. Well, we know that the inverse tan of y over x is theta. So in other words, it is going in the same direction as the radius, or towards the centre. So there's a force, mr omega squared, and it is acting towards the centre. So that's probably the, well, simpler way of proving it rather than using all the vectors and what I did earlier. All right, so another satellite. M is its mass, it's going around the Earth, constant angular velocity. Gravitational force is this expression, AM on R squared. where A is a constant, by considering all the forces, show that R is the cube root of A on omega squared. So just like I was doing with our resisted motion question, I'm going to draw a force diagram. My resultant force, now, in circular motion, that what we call centripetal force, mr omega squared or mv squared on r, is the resultant force. It's the result of the change in direction and so on. Okay? So when we talk about circular motion, this resultant force, it is mr omega squared. I could put either there really. I'm still going to put mx double dot here so we know that I'm talking about my resultant force. So I know this direction, I happen to be picking a point where it's vertical, but it could of course be anywhere on the circle, but it's the direction of the centre. Gravity would also be going to the centre of the Earth, no matter where we are in the circle. So they told us that was am on r squared. They also said neglect every other force, so we're not worried about resistance or anything like that. So the sum of all the forces, the resultant, which we've defined to be mr omega squared, is equal to all the forces, which in our case is just the one, the am on r squared. So it's now a matter of rearranging this and coming up with that expression. The masses, of course, will cancel. If I multiply by the r squared, I'll get my r cubed. We get r cubed is a on omega squared, and it actually drops out very quickly. The cube root of a on omega squared. All right, I've got a piece of string. Use your imagination. 50 centimetres long. We know it'll break if I put a mass of 40 kilograms or more on the string. So I'm going to put a mass of 2 kilograms on it. So clearly the string is not going to break if I've just got it hanging there. But I'm then going to revolve this around my head like a fool and get faster and faster. And then at some point that string will break if I keep going faster and faster. And we want to find the greatest velocity we can put on it without actually breaking the string. So in other words, what's the point that that string will break? So first thing I'm going to look at is, all right, here's my string and it's hanging there. I'll define the resultant force to be going down in this case. That's all I'm doing. Not spinning it yet. I'm just hanging the string down this way. There is a force due to gravity, of course, going down there. Now, here's where we introduce this idea of tension. Anytime you've got a particle connected to, did they actually say an inelastic, sometimes they'll say an inextensible string, or something else, but there will be tension. And tension goes up the string or away from the mass. Okay, it's like a resistance force. So I need to take into account this tension that's going up the string, away from the mass. So there's my formula. The resultant force will be mg, it's in the same direction, minus whatever that tension is. Now, when it's just hanging there, nothing's happening. So I know the resultant force is 0. Right? The string hasn't snapped, it's just holding it there. This is the point where it'll break. So from this I can actually work out how much tension this string can handle. We said the mass was 40 when it will snap. Gravity we're assuming to be 9.8 here. So I know it can handle 392, and the units for force, of course, being newtons. Okay, now I'm going to get this same piece of string, but put a different mass on it, and spin it around in a horizontal circle. So now it's horizontal. What's happening? Well, because I'm now spinning it in a circle, the resultant force will be the centripetal force, which always goes in the direction of the centre. So if this is the end of my string that I'm spinning it around, it'll be going towards the left here. Okay. What other forces have we got? Well, there's still going to be tension in the string. I've got a mass attached to a string. I'm going to have that. There's no gravity in this case because I'm talking about a horizontal circle. So that force doesn't come into play. So it's simply going to be, although I've written it the other way around, that the resultant force, which we know to be mr omega squared because we're going in a circle, is equal to the tension But we've just worked out that it can handle 392 newtons. So 392, the mass is now 2 kilograms. The radius of the string hasn't changed. We can now work out the velocity we can spin our string at. And it works out to be 2 root 98 radians per second. That 2 kilogram mass we can spin before it'll snap. So very similar ideas to what we were doing with resistive motion. But now we've got this idea of tension when it comes to talking about strings. And knowing that if it's moving in circular motion, the resultant force, 1, it'll always go towards the centre, and 2, its value will be mv squared on r, or mr omega squared. So, okay, let's have a go at some of these.